So, welcome for the last talk before the big break today. We already had two quite different talks, and I suppose we will end up with the third one before the larger break. So, welcome, Nick.
Thank you.
Think we are going to take a deep dive in quantum security. So, the stage is yours. Good luck.
Thank you. Yes, good morning, everyone. Nice time slot just before lunch, so I hope you can all make it. 45 minutes. Yes, today we're going to talk about quantum security and what that exactly is and means for our field. I think there are a lot of different innovations. Not this one. Oh, wait. They're two the same. Nice. Okay, now I have the correct one. So quantum security, and before I start diving into quantum security and all its different concepts, one of the brilliant physicists of the last century said, I think I can safely say that nobody understands quantum mechanics. There was Richard Feynman, and if Richard already said that he didn't understand quantum mechanics, then I probably don't, which means you probably won't either. So the pressure is off, okay? That makes it a bit more easy, but it's my task today to ensure that I can understand these concepts to you in plain language, using metaphors, and we will just go through it right before lunch. So my name is Nick. I work as a security architect for a small cybersecurity firm called Netscaper. I'm also associated to the Lectorate of Cybersecurity from the Utrecht University of Applied Scientists. And my fields of interest are, of course, cybersecurity, architecture, risk management, and emergent technologies such as quantum. Today, what to expect? I think I'm going to give you a brief history of quantum physics. Then I'm also going to talk to the core concepts and how quantum computers work. Then, of course, the risks and the opportunities involved. And finally, how cybersecurity is going to look like in a post-quantum world. If you have any questions, save them up for at the end. We can also talk during lunch, after lunch, whatever. I'm here the entire day, so feel free to approach me whenever. So, introduction to quantum physics. If you have read The Hobbit, you know that this is the first sentence of the book. In a hole in the ground there lived a hobbit. And this sentence makes perfect sense. We can read it, we can understand it. It's intriguing, you want to read further. You understand all the words, maybe not hobbit, you don't know what that is at this time, but you will learn later on. But this is a beautiful sentence. If you rearrange the letters, you get something like this. And that makes no sense. And this is also how nature behaves. So in nature, all these different letters, that you can also see here in this sentence, are particles. Oh, that's one too fast. These are particles. Every word is an atom, and the entire sentence is a molecule. Okay? Keep that in mind. I will show you again in this hierarchy. So we have anything of matter, a person, a computer, a chair, whatever. And matter consists of molecules. A lot of them, different kinds. H2O, O2 are probably the most common ones. Those are all different kinds of molecules. Then a molecule exists of an atom, or consists of an atom, or multiple atoms. An atom consists of a nucleus, which is the center, and electrons revolving around it. Then the core of the nucleus exists of protons and neutrons. Remember Jimmy Neutron from Nickelodeon. And elementary particles are there in the end. Those are quarks, photons, and also these electrons. And I see a lot of people already looking at me like, okay, nice, what does this mean? Well, when we talk about quantum and quantum computing and quantum security, etc., we're talking about this stuff here, subatomic. And I think very important to understand this is how nature behaves. We don't see it. We see things classically, we see matter. We don't see the rest. But there are a lot of interesting things happening here, and that's very important to note. So, that was my presentation. Thank you. Okay, we're back. Very short history. It started all with Isaac Newton, 1687, who defined the laws of motion and gravity. Still very, very relevant today. It explains how we can walk, how we can drive a car or a bike. So very relevant. But in his worldview, everything was deterministic. So everything had a cause and effect, and that was clear. Then in the 1900s, Max Planck came, and he said, no, you're not right. Energy comes in discrete packages called quanta. Then Albert Einstein came. He found the photoelectric effect, which basically showed that if you shine light on a surface, it emits electrons. He won the Nobel Prize for that, and not for his theory of relativity. And then another couple of scientists came along. I will skip along those. If you watch Oppenheimer, you probably recognize some of these names, like Niels Bohr and Werner Heisenberg. They had very minor roles, but they were there. They were all very big names in quantum in the early 1900s. And Werner Heisenberg created the first quantum theory. And then a couple of years later, a war broke out. A lot of these scientists went to do other stuff. And then after the war, it got picked up again a bit more. And Richard Feynman was the first scientist in 1981 who released a paper called Simulating Physics with Computers. So this was the first time that somebody actually talked about simulating something and said that we need a quantum computer. So this idea is already over 40 years old. And he said, nature isn't classical, and if you want to simulate nature, you need a quantum computer. So that's why we're here today. So let's talk about some of these key concepts. And before I do, I want to introduce 3 classical concepts first, which we're going to make some, how do you call it? We need those. I'm sorry. Binary digits or bits. Those are the basic units of information that we have today. They're either 1 or 0. Then we have gates, like the AND gate or the NOT gate or the OR gate, that can transform or manipulate these bits into whatever we want. Put all of those together, we can create a circuit, which is basically our standard unit of computation. In quantum, this also works, but you just put the word quantum in front of it. That's actually how everything works there. So we have quantum bits or qubits, we have quantum gates, we have quantum circuits. So if you want to sound smart, just put the word quantum in front of it, that helps. Then I need to talk about superposition as the first core concept. And to do that, I'm going to show you an experiment. A bit difficult with one hand, but okay. I have a box, the best one I could find at the local supermarket yesterday. And we have a cat, a very nice cat. Some of you already know what I'm going to tell you. But I'm going to put the cat in a box, going to close the box. It's closed now. What you cannot see is inside the box, there's a radioactive atom that's decaying and it will emit radiation. That's all you need to know. There's a Geiger counter in there that will pick up on the radiation. And when that hits, it will break a flask of poison, eventually killing the cat. Okay. Now, we know that that's going to happen somewhere over time, but we don't know when exactly. That's how radiation works. So, question to you, how do we know if the cat is dead or alive? Shake the box. That's one way. Open the box. Okay. I will go with that one, but I like your suggestion. Okay, so we open the box. You can see the cat again. It's alive. Very good. Now, I'm going to put it back again. Now, we know that the cat is alive because of our measurement. We observe it. We open the box. We check. We see, the cat is alive or dead. That's how we know, and we determine that the cat is alive or dead. But in the meantime, quantum physics says the cat is both alive and dead at the same time. That's called superposition. And that also means that the atom is in a superposition of states, meaning it's both decayed and not, which also means that the Geiger counter has picked up on the radiation and not, which also means the flask of poison has broken and not. And that concept is super important for quantum computing, because as I mentioned, in quantum computing, we work with qubits, quantum bits. And where a normal binary digit, a bit, is a 1 or a 0, a qubit is both at the same time. And that already brings out tremendous amounts of computation advantages. Now, a qubit is a 3D sphere. Our planet is a sphere as well. You know, this is 3D. It has 3 axes, Z, X, Y. And the qubit can be in multiple positions, right? Superposition. So I've put on a few here and there. And there we go again. Okay. Please move. Yes. Took me 5 minutes to create that animation. So right now we have a qubit that's positioned along the equator of the sphere, just like our Earth has an equator. So it has a 50% probability of being 0 and a 50% probability of being 1. And we have the y and the x-axis to change its phase, right? We can have it on the right-hand side or the left-hand side, and I'm simplifying things a bit here, but that helps if we are going to work with multiple qubits. Because if they have the same phase, they will amplify each other and help us towards the correct answer. If one is on the right-hand side and one on the left, for example, they will cancel each other out, just like active noise cancelling, headphones cancel out the noise. So it's a very common principle, but that's inherent to this superposition and to qubits. So again, measurement is key, because when I measure a qubit or I measure the cat, that's both dead and alive at the same time, it will collapse the quantum state into a classical state. So in the end, we will always have a 1 or a 0. We can just manipulate it into the correct direction that we want it to be. Then another core concept, I'm going to be a bit more briefly about this, is entanglement. And with entanglement, we can correlate qubits to each other. So we create a correlation. What this basically does is it makes sure that when we measure one, we instantaneously, no matter how large the distance, we know something about the other. So it's like sharing of properties. Einstein called this spooky action at a distance. He didn't believe it. So another metaphor here. I have 2 gloves, left and right, I hope. When I ask one of you to get the gloves and hide them somewhere around the earth, and you do that, you come back to me and say, okay, Nick, please have a look. Good luck. I will look. As soon as I find one, for example, the left one, I know instantaneously that the one that's still missing is the right one, right? That makes sense. That's also how entanglement works. So measuring one instantaneously tells us something about the other. And combining superposition and entanglement creates so much advancements and so much more computing power that can do a lot of awesome stuff that I'm going to talk about too as well. So this is basically what happens. With entanglement, we can determine that if a qubit is a 0, then the other qubit must also be a 0. Or the other way around, must be a 1, then the other one must be a 1. So we can create advancement with that. Now, I also talked about quantum gates. In classical, we have the AND, OR, the NOT AND, the NOT OR gates, etc. In quantum, we have a couple of different ones. And I'm not going through all of them, but the most important one is the Hadamard gate. And you can forget the name, basically, it's in the slide. But what this gate does, it puts a qubit into superposition. So we as humans can control qubits and put them into superposition, which is powerful. And then we also have these Pauli gates, the X, the Y, and the Z. And that is, again, that sphere. We can determine whether the qubit must be a 1 or a 0. And we can try to manipulate the probability, or we can try to manipulate the phase. So it's on the left-hand side or the right-hand side of the sphere. And so with all these gates, we can create our own quantum circuit and do awesome stuff on a quantum computer. This is how it looks like. This is IBM System 1. It looks pretty insane, but what basically happens is this stuff is being cooled to almost absolute 0 Kelvin. That translates to minus 270 degrees Celsius. And that is because quantum, and I do this, but it's way more tinier than this, of course. It's very susceptible to noise, whether it's heat, whether it's turbulence, whether it's anything else. It will disturb the quantum state, measurement will take place, and it will collapse into a classical one, so a 1 or a 0, before we could take advantage of all those concepts. So we don't want that. So we have this cooled down, we have all those wires, Some of these wires are used to send signals to the microchip there, so the quantum chip, the QPU, as we call it. And you have other wires going back up to send the reaction, for example, to your classical computer. That's besides this, that's still used to create quantum functions, quantum algorithms, and send them through to the quantum hardware. So that also means that we're not going to have a quantum computer on our desk in a couple of years, right? These are very fragile machines. They exist now only with the larger, cloud providers and hyperscalers. We can access them over the cloud, over the internet, and there we can build our own quantum functions, compile our own code, and try to manipulate these qubits into whatever we want. This is an example of a chip from IBM. I will speed through that a bit. This is the quantum roadmap from IBM, and I think what's important here is that in 2016 they already started with a very small chip with only 5 qubits. Now they have the Eagle, which is 127 qubits, and they try to go to 2,000 qubits by 2033. Those are physical qubits that are actually on the hardware, but we can also create logical qubits, so like the software equivalents, to try to manipulate the hardware qubits. And that will be a lot more. But these physical qubits, they need to be stable because they will give us our computing advantages. Right, so we're also focusing on error mitigation. As I mentioned, very susceptible to noise. Any kind of noise, any kind of turbulence will collapse the qubit into, basically a normal bit. So we're focusing on error mitigation, and we want to go to error correction. So we want to be able to correct the errors before they happen and not just mitigate around of them. That makes it more fast, more advanced. So when you see another news article saying, we have built a new microchip containing 1,000 qubits or 20,000 qubits, I mean, that's nice, but that's not the only thing that matters. It needs to be reliable. It doesn't need to contain, or it should not contain too many errors. It should be error prone. And it should be speedy as well. Okay. A couple of applications, and then we go into the cybersecurity stuff, because that's what we're here for. I will click through all of these. Okay. So quantum computers can do a lot of things. As I mentioned, most of it will be around digging through large data sets or simulating quantum physics or simulating nature. So for logistics, it can do a lot around route delivery optimization and that kind of stuff. For climate change, it can model and predict climate systems way better than a classical computer can do. It will not solve climate change. That's not the case. You will read that somewhere, but that's not the case. But it will definitely help understand it better. In healthcare, it can help with drug discovery, for example, and bring personalized medicine onto the market. And with chemistry, what I always think is very fascinating is it can help with modeling all these modules and atoms that you have in all these chemistry stuff. In metal, for example, it can help us understand why it behaves as it does, and therefore it can also help us understand why corrosion, for example, happens. And corrosion, of course, is sometimes what brings airplanes down. So that's a bit exaggerated, but it can help us understand how corrosion works and maybe even prevent that. So it will make engineering a bit safer. Now we need to talk about cryptography, because here's where the juicy stuff comes in. We have a lot of cryptographic controls currently, banking, VPNs, certificates, basically internet, everything is encrypted. And we're using symmetric cryptography, so private key encryption, and asymmetric. And both will have to mitigate some quantum risks there. So in symmetric cryptography, we basically have Alice and Bob, again, the usual suspects in cryptography, that share one secret key. So in this case, it's very important that that key remains secret and stored secretly, because compromising the key will basically compromise the integrity of the message. When you look at symmetric cryptography, you have a couple of standard or common algorithms, data encryption standard and triple DES. You sometimes still see them, unfortunately. RC4, same stuff. If you work with Active Directory environments, then you see this stuff all the time, unfortunately. but also the advanced encryption standard. So AES and Blowfish, Twofish are also two common examples. Now, they have different kinds of key sizes. How larger the key size, how harder it is to break. That's the idea, but it comes with disadvantages because it takes more computing power. It's not that scalable, so sometimes it's not worth to upgrade to the highest possible bits or key sizes. Now, when we look at quantum, there are a couple of these things that will be touched by something that's called Grover's algorithm. So it's an algorithm that Love Grover, a scientist, created that can quadratically speed up the search in unsorted databases. So when I translate that to human language, that basically means that we can double or quadruple the speed that it takes to search through a database. For example, common passwords. So if we have a database or if a password that says with password complexity, 12 characters, special capitals, etc., and numbers, we know what the amount of options are. With Grover's algorithm and a quantum computer, we can quadruple the speed that we need to get to the right one. So it will make brute forcing a lot easier. So to mitigate that, we already say that for advanced encryption standard, if you are on 128 or 192, please upgrade to 256. That's deemed quantum safe for now. It will probably for a longer time, but that's the way to go there. So symmetric cryptography itself will not be broken by quantum computing. Okay, that's important to understand, as long as you are on high enough key sizes. So this already what I mentioned, I will skip through this. You can read that later if you want. Now for asymmetric cryptography, that's different. So this is what we call public key cryptography. So it works with a private key that encrypts the message into a ciphertext, and we have a public key that is used to decrypt the ciphertext into plain language again. Very simple explanation of this. In most cases, it is being implemented in conjunction of each other. So both are implemented in most systems. Not in all, definitely not all, but in a lot. This should say asymmetric cryptography, sorry for that. But some common algorithms are RSA, digital signature algorithm, DSA, with Diffie-Hellman, and two elliptic curve cryptographic algorithms. They already have way longer key sizes, but the problem here is that they are all susceptible to quantum. And there's another algorithm, it's called Shor's algorithm. I haven't put the name on this slide because you will probably forget it, doesn't matter. Shor's algorithm can break all this stuff because it can solve the mathematics that are underlying all these algorithms. So the mathematics around these are hard enough for classical computers to not break, or at least have a very, very, very tiny chance. But for quantum, that will be made very much possible. So asymmetric cryptography, any of these are all broken by Shor's algorithm. The only thing is that we cannot deploy Shor's algorithm yet because we don't have a powerful quantum computer yet. So all asymmetric cryptographic algorithms are susceptible to that algorithm and to the risks. This is the math around it a bit, but in normal words, as I mentioned, it means that quantum computers make it much easier to break these algorithms. And then we also have hash functions. I will be very short around this, like the secret hashing algorithm that puts a plain text or like a password into a hash. That one are susceptible to pre-image attacks. So you can, with a quantum computer, more easily revert a hash to its input, which should almost be infeasible, actually. But it could with a quantum computer. And they are susceptible to collision attacks. So it's basically possible, mathematically possible, that two different inputs, so two different passwords, for example, lead to the same hash. And you don't want that, because that's dangerous. So also for hashing functions, it means that we need to upgrade the length. That makes it more susceptible, but it's not directly quantum safe. So that's something that's being worked on actively. So if you are still on 128, move to 256 or even to 512. Problem here is, again, that takes it's a longer key size, more computation power, less simplicity, more costs, etc. So don't do this for everything, just for your critical systems. Now, the final part before lunch and I hope I'm still on time, cybersecurity in a post-quantum world. Then we have to talk first and foremost about post-quantum cryptography, PQC. Sometimes it's always is also called quantum-safe cryptography, QSC. Everything is being abbreviated, of course. But it encompasses the efforts that it takes to identify and develop cryptographic schemes that can withstand attacks from both quantum and classical computers, right? That's important. Because classical computers, as I mentioned, will still exist in 50 years and 100 years. We don't have only quantum computers. They will be side by side. So we need a cryptographic scheme that can handle both. So one attack that's already happening at this moment is called a harvest now and decrypt later attack. The problem is you can't really identify this type of attack because we don't know how it ends. So imagine you have a nation-state actor or any kind of threat actor. They steal your data from a database that you left, open on the internet, something like that. They store it somewhere else, safer than you did. And then it's encrypted, of course, so they can't read it. But then the quantum computer comes along in 5 years, 10 years, 15 years. Nobody knows. Very exciting. But then the quantum computer comes, and they can basically break that encryption and still read your data. Now, the problem is, we don't know if this happens. We think it is because it's a very plausible attack. But how do you know if the quantum computer is not there yet? So, although this is realistic, I think you don't do anything different than you do now. You keep your sensitive data protected and safe. If you do that, then this won't work, right? But this is very a real one. And this also implies that you need to migrate to post-quantum cryptography and use your most sensitive systems first. So the National Institute of Standards and Technology in America led the global effort to come up with cryptographic schemes. We have 4 finalists. Give them an applause. Crystal Kyber, Crystal Dilithium, Falcon, and Sphinx. You can forget those names basically as well. But they will replace some of these most common asymmetric cryptographic schemes, like RSA, Diffie-Hellman, elliptic curve. They will have an application for secure key exchange and digital signatures. But it's still very thin, right? There's only one that's basically able to do quantum secure key exchange. So NIST and other organizations worldwide are working on bringing more of these into a standardization effort so that you could use them in your migration efforts. So these are the first, and the Crystal Kyber, Crystal Dilithium, and Sphinx are already standardized and available. So it is already possible to use them, but it's still in a very, very early stage. So, to wrap up things, it's time to start building quantum readiness. And there are a couple of migration scenarios here, just to sum up. For symmetric cryptography, like AES, you need to move to a larger key size where applicable. So don't do this for data that's not sensitive, right? Do this for your most sensitive data, your medical records, your personal records, your HR, your financials, that kind of stuff. When? As soon as possible. Then for asymmetric cryptography, RSA, DSA, elliptic curve, Diffie-Hellman, etc., you need to move to hybrid cryptography. What that basically means, you will combine classical algorithms with quantum algorithms. So you use them side by side. Right? That also helps immediately protect against these harvest now and decrypt later attacks because you have a quantum protocol already in place that encrypts your data. When? Within 5 years. Why? Because we think that 2030 may be the year that quantum computers will become more available. It can be a bit later. You saw the IBM quantum roadmap saying 2033, but we always know that these things come as a surprise. So aim for 2030 is my advice. It will probably be a bit later, but you never know, and you don't want to be surprised. And then for hash functions, as I already mentioned, move to larger key sizes, also only for critical systems. Don't do this for everything. Same stuff, also within 5 years. It's not an immediate threat right now. So to conclude the session, a plan of action, I think it's really important for all security folks to create awareness around this quantum threat, the current threat around harvest now, decrypt later, but also the future threat, which is breaking cryptography, but also businesses I'm not sure where everyone works, of course, but businesses will want to adopt quantum technology because they can provide a lot of advancements, competitive value, etc. So your CEO probably might at some time want to make use of this stuff. So that needs to be secured as well. So default stuff, authentication, authorization, all that stuff will happen as well. I can imagine an OWASP top 10 for quantum in the future. It's not there yet. So for different stakeholders, it's important to create that awareness. Then an inventory of systems and applications that hold sensitive data. It's also important to map dependencies there, because if you do a hybrid cryptography of one, you might break the other system. So it's really important to start mapping this. And we all know how hard this is. So start early, start soon. Make sure that you have budget to do this. So to take this up with your responsibles. And inventory the cryptographic algorithms that they use. So with the previous table that I created, and that's already common knowledge now, you know which ones to move first. So you can basically create a transition plan. Now also include quantum security and risk assessment and procurement processes. If you are going to procure any kind of stuff, an application, YubiKeys, just an example, whatever, that kind of stuff, make sure that they are quantum ready. It's fair to ask your vendors to ensure that they have a plan to make their products and systems quantum safe in the future. That's something that I think you can basically ask them. I'm not sure if they have an answer already, but it will put everyone on edge. And then finally, create a transition plan to migrate quantum vulnerable systems, so basically ones with asymmetric cryptography, to hybrid crypto, and then in the end, but then we're talking in around 5 years' time, I think, start migrating critical systems first, ensuring interoperability. So hybrid, classical, and quantum combined. That's it for now. Thank you, and please let me know if you have any questions. Yes.
I just try to phrase it correctly. So you mentioned a lot about the attack part and breaking crypto, but if you consider things like homomorphic encryption, which is really limited by HPC and the ability of HPC to process that,
Yeah.
do you think that quantum computing or quantum cryptography in general would also play a part in that, like rather in the defense, developing like encryption that betters the way we deal with data?
Yeah, so I will repeat your question briefly. So you're basically asking if we could also utilize this stuff for better defense, so better defensive encryption. So yes, especially with key exchange. As I mentioned, symmetric cryptography, the secret key needs to be stored securely, needs to be sent securely, and that's really a vulnerable process on its own. We can use quantum and basically the entanglement that I've shown you to make sure that keys are entangled and that any kind of eavesdropping attack, for example, get picked up immediately. And that basically will break down the attack. So that's called quantum key distribution, QKD. I decided not to put it on the slides because I've only had 40 minutes, but that's definitely one of the applications that we can utilize this stuff to make sure that our quantum keys or our keys are quantum secure. Yeah, so if you have any interest in that, you can definitely look that up. It's a plethora of information on that. Yeah, thank you for your question. I think you had one as well.
Yeah, so you mentioned that there is a quantum algorithm that can solve the discrete log problem.
Yes.
But it's not possible physically to run it yet.
Yes.
What is the gap between where we are now and what's needed to run this?
Yeah, so the question is, we have an algorithm, the Shor's algorithm, that can break the discrete logarithm problem, DLP. That's the mathematics behind it. There's no quantum computer yet that is possible to break that. So what is the gap? So the fair answer is we don't know. There are a lot of different companies working on quantum hardware. There are a lot of different other companies working on quantum software. So there's a lot going on. Most experts, I don't count myself as an expert, but most experts say between 2030 and 2035 will be the time. But that's a 5-year gap. And if it's 2030, I think we have a big problem. 2035, we will probably be a bit more prepared. But if you really want to run that algorithm, you really need a sound quantum computer that can do error correction and error mitigation. So we're probably thinking 2035 earlier, but that's just a wild guess now. So unfortunately, we do not know. And that's what makes this risky. Thank you for your question. Anyone else? Or everybody hungry? Yeah? Final.
So the 2030 thing is about when, let's say, state-based actors will have usable quantum computers, right? When will I have one in my phone to do key exchange?
That's a good question. I will revert back to my previous answer. I don't know. Going to be very honest there. It's sometimes hard to say that, but that's true. So yeah, when quantum computers become available, that will be probably via cloud providers, hyperscalers, etc., that can be used and abused. When you have quantum key distribution and that kind of stuff in your mobile phones and different other applications as well, I'm not sure. I would say also around 2035 because they lean on the same principles. But yeah, fair enough. I don't know for sure. Okay, thank you for your question. Shall we leave it at that for now? If you do have anything else, then let me know after the session. Thank you. Enjoy your lunch.
Thank you, Nick. Thank you for your amazing talk. I hope the cat is still alive, but I don't know. So for the rest of you, there's an hour break. Don't forget to write your name on the poster. There's a free lunch. Check out the sponsors. Check out the lockpicking village and the capture the flag. There's more than enough time. And we will be back in an hour for the next session. Thank you all.
Thank you very much.
Super.